Hello, today I'll be explaining the basics behind information theory in maths. So what is information theory? Information theory is a field of maths created by Claude Shannon. So information is usually a quality, right? When you go to the shops, when you toss a coin or predict the weather, you all perceive information as a quality, not a quantity. Information theory aims to quantify it, to make information be able to quantify it as a numerical value. That's what information theory is about. So here's a picture of my workbook. So as you can see here, information can be quantified as a metric called a bit. So the bit is like the unit that you use to measure or quantify how much information event has. It finds it out by finding how many outcomes it rules out. If you cut in half like a coin flip, you get 1 bit. If you cut a half again, that's 2 bits and all the way to n bits. Before we dive into the formula for a bit, I want to be sure that you know what a logarithm is. So you know how there's an exponent, right? 3 squared equals 9. And you know how there's also multiplication and division are opposites, addition and subtraction are opposites? Well, logarithm is sort of like the opposite of an exponent too. You can rewrite 3 squared equals 9 in logarithm form. So you can see it's log with base 3, 9 equals 2. So here the base is the same as the one in the exponent, what you exponentiate it from. However, in the exponent, you're trying to find out what is the result of the exponentiation. In contrast, a logarithm is trying to find out by what number do I exponentiate the base to get the number 9. And it's the same for any kind of logarithm or any kind of exponent. It doesn't have to be base 3, it can be base 2, base 10, or even a natural logarithm, which is the base of Euler's number. So back to the formula. Information for a bit equals to the negative logarithm with base 2 for the probability of it. Sometimes we call this a binary logarithm too, by the way. So this is trying to find out 2 to the power of what equals that probability, and with a negative. The negative sort of changes things a bit. So then there's a rule that if there's a negative, it means it's the reciprocal of the result. So here, if the probability was a half, with the negative in front, that would become 2. Alright, let's try a classic example, the coin flip. So we have 2 outcomes here, the head or the tail, which is both 50%, assuming an equal and fair coin. So 50% is the same as a half. So the information based on the formula is equal to the negative binary logarithm of a half. So remember from the rule before, a negative logarithm is the reciprocal of the result. So that means it is equal to the binary logarithm of 2. And since 2 to the power of 1 is 2, there's 1 bit. But what if the probabilities were not equal? What do you think is more informative? Okay, so here's our experiment. So we had 75% chance of heads and 25% of tails. So heads more likely. So the information would be the negative binary logarithm of 3 over 4, which is the binary logarithm of 4 over 3, which is approximately 0.67 bits. For tails, it's the same formula and you end up with 2 bits. So here's what we discovered. The tails was more informative. But why? It had a less probable. It was 25% versus the heads 75%. It proves that more informative outcomes comes from the ones we are more uncertain about. In other words, the more uncertain we are, the more information we get if that outcome proves to be true. So this is a concept in both information theory and Bayesian probability, which I'll discuss in another series. So what's next? Later on in this series, I'll discuss Shannon entropy, Kullback-Leibler divergence, cross entropy, conditional entropy, mutual information, joint entropy, source coding theorem, and channel capacity, and more.